All right, now let's look at an example using the relationships that we had come up with previously for electric field strength. All right, so this will look very similar in style to the warm-up that we did. But here we're taking those same two charges. Q1 is a positive charge, 8.5 microcoulombs, and Q2 is a negative charge, negative 21 microcoulombs. But what we want to do is find the magnitude and direction of the net electric field strength at the 0 centimeter mark. Okay, so we're not looking at the force on Q1, the force on Q2. We're looking for the electric field strength. And what is the electric field strength at the 0 centimeter mark? So remember, when we're trying to figure out the electric field strength and direction, what we want to do is pretend like at this position there is a small positive test charge, and imagine what a small positive test charge would do in that region. Okay, so let's talk through this conceptually, and then I'll have you do the calculations and see what you come up with. All right, so this test charge is experiencing the electric field created by both charge 1 and charge 2. Each of them is creating separate electric fields because they each have different charges, and they are different distances away from the 0 centimeter mark, so we need to treat them differently. Okay, so actually because of that, I'm going to change Q1. I'm going to erase it. I guess I can't. Let's make Q1 blue here. Q1 is going to be blue. All right, so the electric field strength due to Q1, we could calculate it. Electric field strength due to Q1 would be equal to K times Q1 over R squared. So we could calculate this by doing 9 times 10 to the 9, times 8.5 times 10 to the minus 6 over, and what's the R squared here? Where it is 1, 2, 3 centimeters from the 0 centimeter mark, so 0.03 meters squared. Okay, and you can do that calculation. What direction would the electric field be due to Q1? Well, Q1 is positive. It's a positive charge. And so that means a positive test charge would be repelled from it. Okay, so we would say the electric field at the 0 centimeter mark due to Q1 would be to the left. All right, and then Q2, as a reminder, is negative. All right, and it is 9 centimeters away, right? It's further away, but it also has a larger charge, and so it will be interesting to see what the value of the electric field 2 is compared to 1 when Q2 is further away but has a higher charge. So K times Q2 over R squared. Okay, now you can do that calculation where the distance is 9 centimeters. What direction will the electric field be at 0 centimeters due to charge 2? Well, charge 2 is negative, and we imagine what would our positive test charge do when exposed to a negative charge? Our positive test charge would be attracted. Okay. So the electric field due to charge 2 would be to the right. So whatever we're going to do here, we're going to calculate the values of E1 and E2. Whichever one is bigger is the electric field that is stronger, and when we subtract them, we'll be able to not only just find the direction of the net electric field, but we'll be able to find its strength as well. Okay, so E2 is 9 times 10 to the 9 times negative 21 times 10 to the minus 6 over 0.09 squared, 9 centimeters squared, and we end up with 2.3 times 10 to the times 10 to the 7 newtons per coulomb. E1 is 8.5 times 10 to the 7 newtons per coulomb. All right, and so that shows us that the electric field due to charge 1 is larger, right? And then if we subtract E1 minus E2, right, that will give us the net electric field, and that is 6.2 times 10 to the 7 newtons per coulomb. And what direction is that? To the left. Right? If you're to subtract these, the net electric field would be to the left. Cool. Very typical problem that we see regarding electric fields. All right, now let's take a look at our same two charges that we've been looking at this entire lesson. We aren't tired of these charges yet? No, we are not. These two charges, what if they're near to each other? We just found like we can calculate the magnitude and direction of the net electric field over here, right? Just to the left of both of the charges, right? The net electric field is that way. Okay, but how can we visually represent the net electric field at any point around these two charges? Okay, so we have to think, what if we plopped a positive test charge anywhere in this region? What if we plopped a positive little test charge right there? Well, a positive test charge would be repelled from this guy and attracted to this guy pretty directly, right? So the electric field lines would be right there. What if we had a positive test charge right there? Well, it would be repelled away. But then what if that test charge was right here now? Well, it would be kind of like repelled away from the 8.5 microcoulombs, but it would be attracted to the 21 microcoulombs. So that means kind of its net electric field would be kind of like that, right? And as that test charge gets closer, it would just be mostly just attracted. And so we could actually draw some curvy lines here, right? A test charge in general, positive test charge, would be repelled from our big positive charge and attracted to the -1. Right, so we could draw it like that. And on the underside, like so. And then what about up here? Well, a positive test charge, if it was like right here, it would be repelled. But it will also, when it gets up here, it will kind of be attracted over there. So we can draw kind of like something like so. right? Something like so. Okay, and those come back around and come back in. This would just be attracted really, and then you'll end up with little, whoops, wrong direction, little swoopties. Like so. Now I've drawn this fairly symmetrically, okay? But this shouldn't be symmetrical because the negative 21 microcoulomb charge is much larger than the 8.5 microcoulomb charge. And we know larger charges, larger electric field strength means we should see denser field lines. Okay, so I'm going to add in a couple here so we can visibly see that the electric field is denser or stronger around this negative 21 microcoulomb charge. Okay. So what would happen if we had those same two charges plus 8.5 microcoulombs and our negative 21 microcoulombs? What if we had them both positive just for funsies? We made them both positive. How would that change? Well, there would be an awful lot of repelling, right? A positive test charge would be repelled directly out, right? What if a positive test charge was up here? Well, it would be repelled from the 8.5 microcoulomb charge, and it would also be repelled by this guy, so it'd be like doubly repelled, and it would be pushed even further away, right? Repelled, repelled, like that. Similar for this. Repelled, repelled, repelled. Stuff like that. This is a bigger charge, and so we'll draw more field line density. What about here in between? If I put a positive test charge here, right here in between, they would both be repelling. This is stronger, so it would repel it more. So we would say, like, not in the center, but a little bit closer to the positive 8.5 microcoulombs. We could say right there, the electric field is 0, right? At some point that's just a little bit closer to the smaller charge, you would have an electric field strength due to each of these charges that was equal and opposite. And you would actually have a line anywhere on this vertical line. Those electric fields would cancel each other out. And so it's almost kind of like an asymptote situation, right? Where each of these has electric fields that kind of go like that. Okay. Now, what if you don't have positive, like 2-point charges, or what they're called, that we were dealing with previously? What if you've got charges spread out over parallel plates? All right, that'll be the next question that we discuss here in this lesson. Stay tuned.